Welcome to Study Loop.
This is the answer to Chapter 13, problem number 55 from the Smith Organic Chemistry textbook. And this problem says the carbonyl absorption of an amide typically occurs in the 1630 to 1680 wave number range, while the carbonyl absorption of an ester occurs at a much higher wave number, typically 1735 to 1745 wave number. And we are asked to account for this difference. And so I've drawn an amide here and an ester. And so basically, what we need to remember is that the more double bond character these carbonyl bonds have, the higher their wave number is going to be. And so the answer here, as it so often does, comes down to resonance. And so we can draw a resonance structure for each of these molecules. And so in both cases, it's going to be the same. So the oxygen and the nitrogen each have a lone pair. So we could draw the lone pair adding into the carbon-nitrogen bond, and one of the carbon-oxygen bonds breaking, and those electrons are reverting to the oxygen. So again, it's going to be similar in both cases. So it would look like that in each case. And then the resonance structures would look like this. And so for the amide, this is going to be the resonance structure. And for the ester, this would be the resonance structure. Okay, and so in both of these cases, our resonance structure has a positive charge and a negative charge. So we wouldn't expect either of these, either of the resonance structures that I've drawn, to really contribute too much, since there are charges in both. But for the amide, the nitrogen is more basic than oxygen. So N is more basic than O. And so the electrons of nitrogen are more easily donated in to make this double bond. Because remember, that's what basicity means. So essentially, what this means is that the resonance structure here of the amide contributes more. So the amide's resonance structure contributes more than the esters does. Okay, and so what does this mean? Well, this means that in reality, since the structures are going to be a resonance hybrid of these two resonance structures for each of these molecules, since the amide's charge separated resonance structure contributes more, this carbonyl bond actually has more single bond character than does the corresponding bond in the ester, because the resonance structure for the amide, where it is a single bond, the charge separated resonance structure contributes more to the hybrid. That carbon oxygen double bond, it is still primarily a double bond, but it has more single bond character than does the corresponding bond in the ester. And so because of that, it has a lower wave number, because remember, a true double bond is going to show up at a higher wave number than a true single bond. And so the ester's carbon oxygen double bond is more of a true double bond than is the amide's carbon oxygen double bond. And so I hope that makes sense. That was a little difficult to explain. But yeah, so the answer basically comes down to resonance. The amide has a charge-separated resonance structure where the carbon and oxygen only have a single bond, and that contributes more to the resonance hybrid for the amide than does the corresponding charge-separated resonance structure of the ester. And so that's the answer to chapter 13, problem number 55.